So this morning, we are very happy and honored to have Professor Phillip Heiler to give us a webinar. Let me just give a very brief introduction to Professor Heiler before this webinar starts. So Professor Heiler is now Associate Professor at the Aarhus at the Department of Economics and Business Economics. And he is also now visiting the Department of Economics at the Harvard University. Phillip has done quite a lot of very interesting work in econometrics, especially on the causal inference, machine learning, non-parametric statistics, and also the partial identification. So this morning, Phillip will give us a very interesting talk titled Heterogeneous treatment effects found under sample selection. And also he has a very nice application. I think that will be very interesting to the social scientists in our faculty. Now, Phillip, please, the time is yours.
Yeah, thank you very much, Michael, for the kind introduction and also in general for hosting me. It's my pleasure to give this webinar. Well, this morning, or from my side, this evening, I'm sitting in Boston right now, so it's 9 o'clock in the evening. So I'm looking forward to doing this. Feel free to ask any questions during the talk if you have any. Otherwise, there should be enough time at the end to have a good discussion. Yeah, so this paper, Heterogeneous Treatment Effect Bounds under Sample Selection with an Application to the Effects of Social Media and Political Polarization, came out of the work that I'm doing with the Trygfonden Center for Child Research that I'm also affiliated with in Denmark, where we do these kind of large-scale field experiments in the Danish education system, among other things. And they're very often, when we're interested in the causal effect of a particular intervention on certain outcome measures, it's often the case that we have a typical problem of missing data or sample selection. So you can imagine, let's say, the case you're interested in the effect of a pedagogical intervention on, let's say, mental health outcomes. And then you have maybe a survey that is administered through the teachers in class to the students to ask them about, their social relationships and how they feel and so forth. Then, well, the question whether you receive a survey response, of course, depends on whether a student showed up in class and is willing to fill out that survey. And if you think about, let's say, if you're interested in an outcome like mental health, it's very likely that those students who have poor mental health are less likely to show up regularly in class. So you systematically miss students that have a particular outcome, and therefore if you ignore the fact that there's selection into that survey in that particular manner, you basically compare apples against oranges when you just compare the students who did receive an intervention to the units who did not receive an intervention. And of course, this problem is much more general, right? Any outcome that you're interested in that is generated by some selective process, for example, entering the labor market or not entering the labor market, is subject to that principal problem. And of course, there's a rich literature on how to deal with sample selection models or problems, both in economics and other disciplines. But many of the existing approaches require relatively strong assumptions either on the availability of data, so for example, rich information that assure you that you can impose some type of independence or conditional independence assumption that allows you to identify the effects of interest, or some exogenous type of variation that helps you to separate channels that only affect, for example, selection and only affect an outcome of interest. And we are particularly concerned with cases where neither of these are available or are credible to impose. So as Michael said, my research is also concerned with partial identification, meaning when you look at problems like this, you actually do not necessarily obtain a single parameter of interest for what you might care about, but you get a credible set under the maintained assumption. But very often the set is already very informative about a policy question you would like to answer. So this paper is in spirit of that more general philosophy. Now, what I want to do first is I want to give you a flavor of where we're coming from using two empirical examples based on two different papers, including the one of the main paper I'm talking about today. And then I will give you an overview over the the model that we're thinking about in a high level generality and a special case. And then I talk about some of the more statistical problems that arise when you try to solve this problem, and then give you an idea how these things work in finite samples and in particular applications. So the talk is mainly based on these two papers. So there's the 2022 paper that is available in arXiv, for which there's also an R package available and replication notebooks. And then slightly more recent work with co-authors from the Center of Child Research, where we look at exactly that intervention I was mentioning before, of pedagogical interventions and their effects on adolescent mental health in Denmark. All right, so let me give you the experimental setup for the social media and political polarization. So this is based on an American Economic Review paper by Roy Levy, published in 2021. He did much more than I'm going to cover today, but I'm just going to pick one particular question he tried to address in that question, but I heavily recommend checking out that paper. So one research question was, okay, let's say we all worried about generally the effects that social media has on attitudes and opinions. And here I'm concerned with the effect of social media on attitudes with regards to political polarization. So the question is, we look at a particular intervention, and the intervention here is a nudge to subscribe to a particular outlet. So for example, on Facebook, if you're active there, if you subscribe, aka like, a particular news outlet, for example, the New York Times, you're more likely to get, of course, news from that outlet on your feed. And here we're thinking about a particular nudge, so basically a recommendation to say, well, why don't you consider a particular outlet for subscription, but there are no financial incentives or rewards offered if you actually subscribe. So it's purely motivated from, okay, you might get better information, and this might be, helpful for whatnot. So it's a purely a nudge in terms of a suggestion to subscribe to particular outlets. And the treatment itself is counter-attitudinal, meaning, let's say, if you're Republican leaning, then a counter-attitudinal nudge would be a nudge towards subscribing to a more liberal, democratic-leaning outlet, like, for example, MSNBC or the New York Times, and vice versa. If you're liberal, then you would, for example, be nudged to subscribe to Fox News or other more conservative outlets. And the experiment was conducted by recruiting units through Facebook ads. And then some information was collected both through Facebook and through a baseline survey. And then the nudge took place. And then 2 months later, we measured effective polarizations using an endline survey. Now, as you can imagine, if you come 2 months later in an online experiment, there is a potential problem with, units not responding anymore after 2 months, even if they have been recruited for that in the first place. So here, what you see here are the attrition rates for the particular endline survey stratified by political ideology, which here contains everything from extremely liberal to extremely conservative. And you see that on average, from the treatment and control group, about 50% are actually missing from the endline survey. And also that there's quite some substantial heterogeneity between the treatment and control groups and across the different groups within treatment and control group. So the response rates, they range between 54% to 35% in the different strata that you can construct here. And of course, this causes a problem, right? Even if you just look at within a particular group, well, you have a lot of missing units. It might not be completely arbitrary who did not respond to that survey, but it might be units who might get a particular return from that nudge in one or the other direction. And there's also differential attrition between the treatment and control group. So even, let's say, if it would be not systematic within a particular group, it would be systematic maybe potentially between treatment and control units because, well, you change the information available to them on social media. That could, of course, affect whether they come back to you in the survey that is administered through that. So, but one more thing I want to point out here is that, okay, we have this heterogeneity here in the response rates. And this will actually be key to how I will be thinking about solving or providing a solution to address this. Another example is an experiment that we run in Denmark, which is concerned with a co-teacher intervention. And a co-teacher here is basically a second teacher that joins in 6th grade, almost throughout the whole school year. We looked at, of course, many different outcomes here. I focus on the mental health. And it was a stratified randomized experiment where we had 35 schools in 3 different treatment arms. So one treatment arm was the control group, and the other 2 treatment arms were either basically a pedagogically qualified co-teacher or a more social worker type co-teacher that was helping with the classes to an extent of either 14 or 10.5 hours. So depending on the qualification level, they stayed longer or shorter officially in the schools. And there, what we did is, okay, we ran this experiment, but for the evaluation, we're actually using national available surveys for various reasons, right? So they are administered through the schools. There are no data protection issues here, and there's also no risk of potential interference by us, for example, administering our own survey in class, and we can guarantee also the comparability across different cohorts. But on top of this information, we have the rich Scandinavian register data, which allows us to use unique identifiers to combine information from, children and parents together to really have a rich description of the socioeconomic background and much more. Now, here in the particular intervention, we found a similar, though not as large of a attrition problem or missing data problem that we had in the previous study. So if you look at the full sample, we had about 78 in the control group that filled out the survey, while in the treatment group, close to 90% in both arms. So the intervention here, at least on average, had definitely a positive effect also on the response rates. So now you can imagine, well, of course, the student makeup in this 90% group is different than the student makeup in the 78% group. Now, on top of that, it also varies within different strata that define, for example, socioeconomic status of the students. So here's just one example. If you look at the employment status of the parents, we see quite some substantial variation between different groups. So the largest, the high socioeconomic status where both parents are working in the particular treatment arm with teaching assistants without degree, they had a over 90% response rate, while for the lowest socioeconomic status in the control group, they only had about a 65% response rate. So there's definitely heterogeneity in these response rates. Now, on top of that, here you can definitely hypothesize that, well, there's likely also a different effect of such an intervention on the outcomes, right? If you think about students who are from a poor socioeconomic status, having an additional teacher might have, for at least a certain amount of time, might have a very different effect on the outcomes compared to someone who comes from different family background. And we're in this paper basically trying to exploit the combination between these 2 things to say something precise about what's going on. So overall, in the paper, I look at a very general method that can be applied to non-parametric sample selection models, so without imposing functional form assumptions on outcomes or the selection step or whatnot, and works in very data-rich environments, meaning in setups where the selection into treatment and the sample selection step can also depend on high-dimensional confounding variables. So many socioeconomic background variables, transformations, nonlinearities, fixed effects, and the like. And to operationalize things, we're using a debiased or double machine learning approach that allows us to get regular inference. So meaning we can make statements about hypotheses that we would like to test and have theoretical guarantees with that. And the procedure works basically as follows. We first start with a very general problem that's high dimensional, and then we want to learn something, well, maybe first about an aggregate population. And this is to a certain extent a solved problem in the literature, but here I'm interested in the question of heterogeneity, because very often when you run these approaches that I'm talking about here, for the average population, you often don't find any interesting results because positive and negative effect cancel each other. You have a significant missingness, so therefore it's very hard to really extract something in many examples. But if you look at particular subgroups and you do that in a clever way, you might actually say quite a lot. And the idea is to say maybe a general problem could be very high dimensional, but the level of heterogeneity is lower dimensional. So basically, at the end of the day, what we're doing is we're using this high dimensional information and essentially project it down to something smaller that we can work with and what we can develop theoretical guarantees for. And then on top of that, in this setup where we have set or partial identifications, where we don't pin down the parameters of interest exactly to a point, but get a credible interval for it, there are some delicate issues that you have to solve to get guarantees with regards to statistical inference. So here I propose some misspecification robust way that allows us to have guarantees even if certain assumptions are violated, and we have particular types of misspecification in our models, and some extensions of that. And then the application to social media, and then the R package, which is available on my homepage. In terms of literature, just briefly, the strategy of identification in sample selection model goes back to a rich set of papers, in particular Chang and Rubin and Lee, who first looked at problems of sample selection under a monotonicity or additive separability assumption in the selection equation. So that imposes a little but not very strong structure on how units are selected into observation. And in terms of inference, we're using recent ideas by Jörg Stoy and Andrews and Kwon, which work in either in a moment inequality framework or in the context of a vector of parameters that have certain distributional properties to get more powerful inference results compared to naive inference approaches. And then in terms of heterogeneity analysis, we're using essentially a combination of non-parametric projections based on the idea of Januzhukov and Semenova in the Econometrics Journal 2021. And in terms of the incorporating the high-dimensional confounders in this particular problem, the first paper to provide moment functions that allow us to do so was the Semenova 2023 paper in the context of what we refer to as Lee bounds, so monotonicity-based bounds in sample selection models. All right, so let's look at the model in a bit more detail. So this is the kind of high-level setup, how you can think about it. So let's say, as an example, we're interested in some outcome y and the effect d y. And then what we actually observe is this ys, where s is an indicator for whether the outcome of the unit is actually observed. So s could be, for example, you're responding to the survey or not, and y could be your latent mental health, right? So for some units, we actually observe the mental health, and for some units, we don't, according to this S. And then the S, of course, could be affected, well, by some observable variables that we have available, for example, the socioeconomic status of the parents, also by our treatment, right? If we put resources in school, that could well affect whether students will respond to a particular survey. But also, and this is the crucial part here that makes the problem hard compared to kind of missing at random type of problems, is the presence of unobserved confounders, which can also be correlated with the observed confounders that are both related to outcome and selection. Yeah, so for example, let's say if there's an underlying mental health process that decides whether you show up to school and how you feel in general, then this U covers that and causes a systematic selection into a systematic selection. And then, of course, then comparing treated and control units is no longer representative because of that type of selection, even if you condition on all the observed covariates. Now, so classical imputation, weighting approaches based on conditional independence of selection given covariates don't work here anymore because their fundamental assumptions are violated. There's more going on than just what you can explain or condition on via using these X variables. In the particular example, what we would have is that the D would be the nudge to news subscription, which might be allocated based on political ideology, which might be here an X. X can be other observed background characteristics obtained from Facebook or the survey. U could be unobserved background characteristics. And Y could be the unobserved polarization measure, so that everybody has a level of polarization, but we only observe them for the units for which S is 1, meaning we are selected into the end-line survey. They actually filled it out after 2 months. Now, so we have to work with YS. We cannot work with Y. Now, if you're in this setup here, you can think about this in terms of what hypothetical worlds exist here when the treatment is exogenously set to either 1 or 0 here, right? There's just you being nudged or you're not being nudged. And if you think about, okay, which variable are caused by D, there are two variables which are, bless you.
Sorry,
there are two variables.
sorry.
That's all right. There are two variables which are caused by D immediately here. It's the outcome itself and its selection. So if we look then at a world where we fix D exogenously to some value, then there are two potential outcomes, YD, and two potential selection statuses. So we would denote these as, in the typical Rubin-Neyman notation, as Y1 and Y0, and S0 and S1. So every unit has these four variables, these two pairs of potential selection and potential outcome values. So if a certain world is realized for them, so if I put you into the treatment group, then you have what is realized is your outcome in the treatment group and your selection in the treatment group. So that means if you look at the implied what Frangakis and Rubin termed principal strata are in the setup, it's very similar to the kind of binary IV case where we have 4 principal strata. And we're using the same name here as in the Imbens and Engrist IV type of literature, but they have fundamentally different meaning here. So every unit is characterized by this pair S0, S1, and of course, since it's binary, there are only 4 combinations which can exist. You can be an always taker, which is someone who will always respond to the survey, no matter whether you put them in the treatment or the control group. You can be a complier, meaning someone who will not respond to the survey if he's in a control group, will if you're in the treatment group. A defier, someone who will respond if they're in the control and not in the treatment, and a never taker, someone who will just never respond to the survey, no matter what you do. So these are the fundamental types or principal strata that we care about in this setup. So if you, for example, let's say if you would look at only the selected units, you see it's the composition actually of always takers and compliers. So, and it could well be that in the control group now you have a different mixture of these than in the treatment group due to this systematic selection that I alluded to earlier. So what we actually would want to look at in the sum selections are causal effects that are defined for these principal strata, so these subgroups. That guarantees us that we're not comparing apples to oranges. Okay, so how do we now move forward to actually say something about causal effects of interest in this setup? So we're going to do two things. We're going to first impose something that is guaranteed by the randomization, or maybe an assumption that you could also make in certain observational studies with regards to the treatment. So we're basically saying that the allocation of the treatment is not the problematic part here. And so, for example, if you're in a randomized experiment, of course, that's guaranteed. You can allocate a treatment as you want. But if you go to observational data and you're looking at the causal effect of some observational treatment, you have to argue for that in a particular instance. So we're saying that the treatment is conditionally independent of potential selection and potential outcome, as long as you condition on the observable covariates. So in the randomized experiment, you can even guarantee that it's fully independent. Again, in an observational study, you would have to argue for that. But so this is a strong assumption. So this definitely doesn't apply to all treatments. Now, this is implied by the structure, for example, that we saw in the directed acyclical graph just earlier, but we can also just start from that point here as a slightly weaker assumption than as compared to just imposing the graphical model I showed you before. Now, if you would just take this, you could in principle already get bounds, but under just this assumption, bounds for the causal effect for this principal strata will be extremely wide. So they will generally be uninformative, for example, about the sign of an average treatment effect. So you cannot even say whether the policy had a positive or negative one, let alone pinning it down to a smaller interval in a particular direction. So therefore, we want to impose a little bit more than that. And a typical assumption that has been suggested in that literature is to say, okay, maybe we restrict the selection behavior slightly. So one restriction you could think about just as a starting point, and we're going to relax that in a little bit, is to say, okay, let's assume monotonicity for strong monotonicity here would mean intervention makes everyone at least as likely to participate in the survey. Yeah, so let's say if I put resources in school, an assumption that I can make, but I cannot test, would be, well, if I put more resources in school, students are at least as likely to fill out the survey compared to when I don't put additional resources in school. And of course, this you have to argue whether this is credible, depends on the particular intervention. Now let's take this as a starting point. Now, if you have a monotonicity assumption, the advantage of that is that you can actually identify the shares of the different principal strata, so these subgroups defined in terms of their selection behavior in the data at hand. And that, as a result, allows you to get sharp bounds for the causal effects for these principal strata as well. So, for example, let's pick the always takers. I will talk about them throughout the talk because they tend to be one of the most interesting groups in many applications. But all what I discussed today can also be extended to bounds using for other principal strata. So the causal effect for the always takers would be the expected difference between the potential outcome under treatment and the potential outcome under control for the units that are always responding to survey, no matter whether you put them in the treatment or the control group. And of course, these effects can vary by the observable covariates. Now, so these are conditional average treatment effects for the always takers. Now, under monotonicity, you can show that a sharp lower bound, for example, you can also do this with an upper bound, but here's the lower bound, can actually be identified from the data. So the lower bound here is the difference between two expectations. Let's focus on the second expectation first. This is just the expected outcome for the selected units in the control group, a particular value of X. So of course, this we can just obtain by looking at the outcomes for the control group that are selected into the survey. So this we have. Then left part is the expected outcome for the selected treated group. So this we also have. Conditional on the outcome being smaller or equal some truncation threshold. That truncation threshold is defined by some relative probability P naught that essentially comes from these shares of the different types that I discussed. So this you can pin down thanks to the monotonicity assumption. So basically what it does is it says, okay, we know that in the treated selection group, there's a mixture of different types. Let's be as conservative as we can be and say like all the most extreme values come from the type you're not interested in, and all the moderate values come from the type you're interested in, and vice versa, depending whether you look at a lower or an upper bound. And that gives you this sharp bound, no matter what the actual composition is actually in that group. Now, in principle, this is already available in the literature as an identification result. So you could say, okay, this already solves the problem, right? I can get heterogeneous causal effect for these different principal strata. Now, the problem in application is the following. Well, if you have many X or continuous X, it's actually extremely hard to obtain these quantities, right? Think about a typical data set. You have 30, 50, 100 whatnot covariates, then this is an extremely high dimensional quantity, similar to how you think about, for example, conditional average treatment effects in standard problems where you don't have a sample selection problem. There we know that it's actually not possible to conduct regular inference on these in high dimensions. So if X is high dimensional, we have a fundamental restrictions on how precise statements we can make about, for example, an hypothesis about the sizes of the effects or comparison of effects. So this is one problem, and of course, which X should you look at is another problem. So now the idea in this paper is the following. Let's say instead of looking at all the X's, let's look at some summary measures. So for example, in the application with the co-teachers, we have very rich register information available for all the students and the parents and so forth. But let's just find some summary measures that are good description of the socioeconomic status of the students, optimally ones that we can actually act upon. So for example, if we have if you're thinking about implementing an intervention in class and we look at characteristics, for example, the average share of students with parents from a poor socioeconomic status, that's something we could observe and based on which implement an intervention. So this would be in general some variable z that is just a function of the observed covariates. A function could just pick one of the x's, could pick combinations of the x's, but in general, this z cannot be too high dimensional. Okay, so it can be it can be of higher dimension than 1, but it should not be as high of dimension as the x potentially can be. So x can even be larger than n, and even potentially be much larger than n, but z is low dimensional. So you can think about this more as a non-parametric problem at the end of the day. Then what we're doing is, okay, let's look at causal effects for these subgroups. Okay. Now, why can we say a little bit more here compared to, let's say, unconditional effects? Well, the main insight is that in this setup, unlike a classical point-identified problem of conditional average treatment effect estimation, here we actually have two types of heterogeneity. So we would expect a classical type of heterogeneity, units that have different background characteristics. Then the intervention might be differently beneficial, of course, but also the severity of the identification problem, so the sample selection problem itself, might be harder or easier for some units, right? Imagine a student who essentially always shows up to school and is very, excited about filling out a survey. For them, it's very easy for this type of student, it's very easy to measure an effect, right? So you get something very precise for that subgroup, while for some other units, you might not. So in the combination of the two things actually will help us to say something. So this is the most important slide. If you understand this graph, you understand everything I'm doing in this whole paper. So here, this is a simulated example to just illustrate how the method is working. On the right plot, you have a graph that shows you the true conditional average treatment effect curve for the always takers. So this is the true line that I know here because I simulated the data as a function of z. Z here could be pre-treatment covariate, for example, the socioeconomic status measured of the parents measured on a continuous scale, or let's say the performance of the students in school before you enacted the intervention. Then, of course, you cannot point identify this curve here under the assumptions that I imposed, but you can get bounds for it, the sharp bounds that I just showed. Now, if you use unconditional methods that do not consider heterogeneity here, you would get what the left plot shows with regards to these lines. So you see the sharp bounds here would be straight black lines. Of course, they don't vary across C, and you see that 0 is included here in the black interval here. The dashed black lines are the associated confidence intervals. So here in this case, you would not reject the null of no significant treatment effect for any type. Now, the red end here shows the method suggested in the paper, which is the bound for the causal effects as a function of z. And here you see two things happening. Well, the bound itself, of course, moves somewhat with the actual location of the treatment effect. So there's somehow a location shift that happens as c changes. But on top of that, also the width of the identified set, right? So the width of the red band changes as the heterogeneity dimension C changes. So you see the band getting increasingly narrow as we move to larger Z values. And this in combination leads to the result that, well, here, for example, for this area between 0.8 and 0.5, we would actually detect significant negative effects, while here for the area of 0.95 to 1.0, we would detect significant positive effects, which is in line with the actual true effects that we see over here. So basically, by the fact that here we can measure something precisely, and it also has a different location, and this we can measure also somewhat precisely, but also has in particular a different location, allows us to say much more than just using this naive, constant, unconditional bounds. Now, on what you also see on the right plot here, it looks almost the same as the dashed blue curve, but it's not. So this here is a uniform confidence band for the whole curve. So if you're interested in testing a hypothesis about the effect at a particular z value, you can use these confidence intervals that are in blue here. They also have some misspecification robustness properties that I will talk about later. These uniform confidence bands don't have that specification robustness, but they allow you to test a hypothesis about the whole effect curve. So you can test for constant treatment effects and they're like using the whole curve or differences at any value of C straightforwardly. Okay, so then let me get a little bit more technical and talk about the actual assumptions that I'm imposing, and then how the estimation and inference procedure works, and what do we have to pay attention to in this partially identified setup compared to standard statistical testing problem. So I talked about homogeneity earlier. So now we're in the paper, we're actually assuming something weaker, which is called weak or conditional homogeneity. Here now we're not saying that the treatment makes everyone at least as likely to participate in the survey or to be selected into the sample. We're saying that, okay, well, the effect goes weakly in one direction, but the direction can vary based on the X values. So it could, for example, be that, let's say, high socioeconomic status students will be strictly less likely to respond to the survey if you make an intervention in school, and low socioeconomic status student would be weakly more likely to respond to the survey if you do so. The point is that these different, the direction, the weak direction of that particular effect of D on S has to be, you have to be able to classify that based on observables only. It's a relaxation of the earlier condition, but there are data generating processes which would violate that. So it doesn't allow for all types of selection, but for a very rich class of selection behavior. We also assume that we have comparable units, at least in large samples, between the treatment and control units in the selected sample and in the treatment and control group. So this is pretty standard in any causal inference problem, right? You need to be able to make comparisons in large samples. And then we assume, so this is a margin condition here allows us actually to do this classification at a particular speed in terms of how much data we need for it. You can relax this with some technical details, but here I just assume that you can well separate the distributions, the conditional distributions of treated selected and control selected for each X. So there's not like too much units floating around at being basically indifferent in terms of how the treatment affects the selection behavior. But you can relax that, and I have some follow-up work where we do this much more rigorously. And then continuity, this is just to have a unique identified set, because we're using these quantiles that I showed earlier for trimming for the first part of the bounds, and the continuity assures that the trimming bounds are uniquely defined. Okay. Now let's talk about how we actually implement the procedure. So I will first show you the recipe, and then I will show you theoretical guarantees based on that. So the idea is actually pretty easy. If you think about a classical problem of estimating conditional average treatment effect, so for example, Michael also has some work on that. One approach is to say that, well, you take a approximately unbiased signal for a conditional average treatment effect in high dimensions, and then you want to find out its conditional expectation now given these low dimensional summary measures Z. So basically you project it down onto something that is less complex. So this has been also suggested in various papers like the Semenova and Zhukov paper. Now here it's a little bit more complicated because you don't actually have an unbiased signal for the conditional effect of the always takers. But what you can get is you can get an unbiased signal for the conditional effect times a factor that is proportional to the density of the always takers. So essentially the probability of being an always taker. And luckily, using standard methods, you can also get an unbiased signal for this density itself. So therefore, you can essentially construct a ratio by using two non-parametric projections. So, and these projections are based on these moment functions psi here that have different subscripts. Details are not that important. The point is that these functions only depend on the data and on some nuisance quantities that I will talk about in a bit. So this you can get from data. Then, well, just have two expectations, right? So of course, conditional expectations you can get by estimating that using a flexible, for example, regression approach, where the flexibility in the z variables increases as n increases. So you have, for example, basis transformations, polynomials, and the like that you can use to approximate this using actual data. Now, under weak conditional homogeneity, things becomes a little bit more complicated. You get a sum of two ratios, but it's essentially the same intuition. So you run multiple non-parametric regressions using these different signals for the different components here. So step by step, how does that work? Well, first we construct these moment functions that identifies again these kind of scaled conditional bounds and identifies the or is an unbiased signal for the density itself. And then we just use the fact that z is a function of x, so it has not more information than x to do this non-parametric projection. And these non-parametric projections are essentially flexible regression models where we take the moment functions as dependent variables. Like in a standard regression model, you take y, you regress it on x. Here we're taking these moment functions themselves and regressing it on flexible transformations of the heterogeneity dimensions that we're interested in. So here you could also, if you want, impose some model structure and say, well, I'm just going to look at heterogeneity as a linear model and just regress it on z and a constant maybe. But if you want to do it flexibly and adapt to various shapes of heterogeneous treatment effects, then of course you can use transformations and keep increasing their complexity. And in practice, you can choose, of course, the number of transformations using data-driven methods like cross-validation and the like. So at the end of the day, what you get is a linear projection part, and then you get an approximation error, and then some error that does not vanish. And then you just use essentially predictions from multiple of these models and construct the empirical analog to the ratios I showed earlier. And then based on that, you can use the robust confidence intervals that I'll talk about in a minute. Now, in practice, here these nuisance functions that you need to basically have the dependent variable of all these regressions, they also have to be obtained from data, and there it's where we use debiased machine learning. So basically, if I go to the moment functions, contain different quantities that are defined in terms of the joint distribution of the observables. So, for example, the propensity score is part of that, or the conditional selection probabilities. And on top of that, the conditional quantiles of the selected distribution in the treatment and the control group. So in particular, say in a randomized experiment, you know E of x, you don't have to estimate it. You have to estimate the selection probability and these conditional quantiles. So in the classical case, you would have 4 nuisance parameters that we need to estimate. But this can be done using standard supervised learning methods at the end of the day, or general statistical methods like quantile regression or logistic regression, whatever you think is most appropriate for the particular problem. We have to do it in the same way as in the classical debiased machine learning framework, where we would cross-fit this. So we would take part of the sample and generate a model for the nuisance function on that. But then for the actual moment function, we are using the holdout sample. And then we're doing that for all the different combinations in the data, such that we guarantee a certain form of independence of the actual model that generated these nuisance functions and the data that we use in the particular moment function. Now, so this is exactly the same as you do in the standard Chernoshukov et al. 2018 debiased machine learning approach. Okay, so then quickly theoretical guarantees, and then we talk about inference. So let me just briefly talk about one assumption that is crucial. So most assumptions are pretty basic and parallel to standard debiased ML and non-parametric regression literature. The only thing that differs slightly is that we need other rate guarantees. So we need here LP convergence guarantees for these nuisance function estimators. So those are available for many algorithms in the literature, like neural networks and random forests and regression models under different assumptions, high-dimensional sparse parametric models, and we need L1 and L2 rates. In the standard setup, you would not need L1 rates. This comes to the fact that we have this trimming indicator, which introduces a particular structure that requires different convergence guarantees. Now, what we also need is that these LP rates are sufficiently fast. So if you compare that with classical statistical inference, basically this KB, which is the number of transformations of the Z variables that we have, does not enter the problem. So then in the standard world where we don't do heterogeneity analysis, we usually require that the mean squared error rate of the nuisance function is sufficiently fast, of slightly faster than n to the power of -1/4, which can be achieved by many methods under credible assumptions. Here we need something slightly faster. So the K increases in the number, it decreases in n. Therefore, the overall convergence rate of the nuisance function has to be slightly faster compared to unconditional ones. Typical KB is relatively slow in n. The rates increases are not that quick if the dimension of C is moderate. Okay, so under these assumptions, we get that the upper and the lower bound together follow a bivalent normal distribution after appropriate standardization. So if you take, you can do that either around the local projection. So if you just run a regression, but you don't necessarily assume that the heterogeneity is correctly specified, you still can get asymptotic normality around the linear predictors, just like you would do in a standard regression model, where even if, let's say, you assumed homoscedasticity or something like that, you run a regression. Well, okay, you have to adjust the inference, but your beta parameters will still be consistent around the linear projection, true linear projection. Same as here. Now, if you make the non-parametric model flexible, so you get the C dimension grow to adapt to these various shapes, as I showed you in the plot as well, which is covered by this condition here, then you actually obtain bivalent asymptotic normality around the true and lower bounds that we defined earlier. Now, in principle, you could stop here now and say, okay, well, this is all I need. Well, if I want to conduct now inference on the bounds, I can just use this normality result, construct confidence interval in the usual, plus minus 1.96 standard errors type of fashion. And for the effect, you could also say, well, I could do the same thing, right? The effect has to be somewhere between the bounds. So therefore, I can use the bounds as kind of an implicit quantity to talk about the inference on the effect. However, there are some delicate differences here, and there's a very rich literature in partial identification to delineate that. So there's a difference between testing an hypothesis about the effect and testing an hypothesis about the bounds themselves. If you think about a problem, let's say you have an upper and a lower bound, true parameter is somewhere in between. Now, if let's say the upper and the lower bound are very far away from each other, then of course the uncertainty in the lower direction primarily comes from the lower bound, right? If you think about they're normally distributed, so if you think about a statistical risk around a particular point, in the lower direction, it mainly comes from the lower bound, where in the upper direction, it would mainly come from the upper bound. So in principle, if you think about it as a testing problem, it actually becomes closer to a one-sided testing problem if you're interested in the effect. Now, the other direction is, let's say, the identified set, the upper and lower bound, are very close to each other. So the identified set is close to a point. Well, then if you think about statistical uncertainty, they essentially overlap. So therefore, both in the lower and the upper direction, there comes uncertainty from both in there, meaning you have effectively something close to a two-sided testing problem. So therefore, the width of the identified set actually has properties on how we should think about which critical value to use, and we can improve power by not just blindly using two-sided critical values all over the place. This is the first thing. Now, the second aspect that I want to take into account here is that, well, if I look at unconditional bounds, there might be a misspecification, of course. I might not get the propensity score correct or the selection probability is correct, whatnot. But maybe on average, I'm doing okay. So these unconditional bounds are fine. Now, if I'm looking at heterogeneous bounds, of course, I have the risk of local misspecification, right? Let's say in a certain Z range, I might get the curve not exactly right there, even though on aggregate, it still fits kind of well. Maybe I chose it via cross-validation using some global criterion, but it was not really good tailored to a particular Z region. So therefore, in the worst case, what could happen is that your bounds would suggest an empty identified set, or they could even cross in the worst case. And so the question is then, okay, how should we think about the inference on the parameter in these cases where the identified set is extremely narrow or even empty as well? The idea is here basically to exploit, to relax the underlying inference problem and to say, okay, maybe we're not we're not picking just the moments as face value, but we're basically relaxing them by a little delta and take the ones that agree, that just the smallest ones that still agree with the data. And then based on that, we define an implicit parameterization that is always guaranteed to exist, even if the identified set is empty. So this essentially what it does is there's an implicit pretest, that's how we can think about it, that basically tests whether the upper and the lower bound are equal, right? If they're equal, then the identified set is just the point. So this is basically what would go on if you do a wall test that tests for equality of the upper and the lower bound. And what we're doing is we're taking this parameter and we're augmenting the parameter space by this kind of pseudo parameter. And then we're conducting inference over this extended set using a combination of two confidence intervals. And maybe for the reason of time, I'll skip the technical details. The idea is basically to combine two intervals which individually are invalid, but whose estimation errors cancel exactly at the right size, such that we can guarantee at least 1 minus alpha coverage with the resulting confidence intervals. And this we can all simulate by using the bivariate normal that I showed you earlier. Okay, so then we use that approach and we conduct inference then on the additional effects. We have an inference guarantee that says, okay, the probability that a true parameter is in the confidence interval is at least 1 minus alpha. Now, so inference here generally is conservative, but we have a size guarantee, meaning we will not do worse in large samples than the nominal size of an underlying test at the level 1 minus alpha. Yeah, so we have a coverage guarantee that we like. Now, you can also extend this to the uniform confidence intervals. There, the approach is based on a bootstrap, a weighted bootstrap. It's very standard, so I'm going to skip that here. And we have also the theoretical guarantees for the bootstrap procedure as well. Okay. Now, let's look a little bit at the finite sample properties, and then let me briefly talk about one of the applications. So here's just a simulation to show you what are the properties that you get in finite samples when you apply that. So here I'm using a standard sample selection model, and where I know the truth. So you saw that earlier in the plot already. And I'm choosing to estimate a nuisance function using generic machine learners. So here I use a generalized random forest and twofold cross-fitting. So I only split it once to generate the models for these nuisance quantities. So this is the DGP. It looks like a very standard generalized Roy model where we have a sample selection step where the treatment enters. And here it's a very simple DGP, but I'm not actually imposing the knowledge of it, right? So I'm estimating this using machine learning methods. I'm not using a parametric model that is correctly specified or anything like that. Now, interested here, of course, in size. So if I do my test along a particular z dimension, now what type of coverage do my confidence intervals have, and power, so how much can I reject a wrong null hypothesis. In terms of size, here for different DGPs, one with 10 regressors, one with 100 regressors for sample sizes 400 and 2000. You see that coverage, at least in the larger sample, is to be closer to 1, but definitely above the 95% nominal level. It's also pretty solid in small samples, except close to the boundary. And even in the harder design with 100 covariates, we have similar behavior. So coverage overall tends to be conservative, but most of the time over the nominal level. So theoretical approximation seems to reflect pretty well what's actually going on in the finite sample world. In terms of power, you get a very typical power curve with one exception. So here the null is true at 0, and as you go away from it, the true parameter is further away from what you're testing. Here you have basically a size very close or equal to 1, so you don't reject null if the null is true. And then power, this is because of the conservativeness of the method. And then if you go beyond that, power increase is kind of typical for a normal-based test, normality-based test, and converts to 1 as soon as your effects are pretty large. And it's easier to reject the null for effects that are large if you have more sample size and if the number of regressors is smaller, so in lower dimensional setups. Okay, then let's go through the social media and effective polarization application. A little bit more detail on the process here. So I already explained the experiment earlier. Now let's talk a little bit more about the particular outcome. So we're interested here on the effect of this counterintuitional nudge on effective polarization. And effective polarization does not measure how much polarized you are in terms of opinions. So in terms of how much you, for example, think the state should spend for the military or for social welfare or anything like that. It's about what you think about the other side. So there are questions asked along the lines of, okay, how would you feel about if someone of your family would marry someone from, a different political spectrum? And different questions like that basically try to elicit the attitude towards the other side. So it's more about, how do you feel about the other side, not whether you agree or disagree on the substance of the political questions. And I'm picking that outcome variable because in the original study, Levy found a decrease in effective polarization, so less polarization in terms of this effective measure based on counterintuitional nudge. However, when he corrected for the attrition, the significant attrition, using generic methods like unconditional Lie bounds and linear regression and conditional Lie bounds using a parametric model, he didn't find any significant effects, and also heterogeneity was mostly insignificant when using standard parametric linear regression type of models. Here you see the results now for the causal effect of the intervention using both the methods in Levy and the device machine learning DML type of bounds, where the nuisance functions are estimated using different models. So here I use parametric models, logistic regression, linear quantile regression, and here I use the generalized random forest. And the unconditional effect in the original analysis was minus 0.05 standard deviations, and the conditional ones about half the size. Now, if you apply bounds in the original study, they're very, very wide and essentially uninformative. The unconditional bounds, also using the deep bias machine learning approach, include 0, so you cannot reject the null hypothesis of no effect. They are significantly sharper than the bounds that would be obtained under conventional methods, right? So it's about 40% shorter, the identified set here compared to conventional methods, and only barely includes 0. Now, bigger condition effects, things become more interesting. So here, this is based on political ideology. We can see that we have these identified sets and the associated misspecification robust confidence intervals. We see that in particular for conservative users, there's actually a significant depolarization effect here. Now, of course, the original experiment was not really powered to do that type of a detailed analysis. So, of course, confidence intervals tend to be pretty wide, but this is just because of the, how much data was available in the experiment. But at least you can say something. In terms of age, there's also an interesting picture. So we find that, look at the age ranging from 18 to 90, that the identified set is close to a point and much narrower for very young users. And negative as well. So the interval here is suggestive of a depolarization effect for younger users. Also accounting for the statistical uncertainty, 0 is in the confidence interval. If you look here at the dashed lines, but we know the inference method is conservative, right? So I would say this is kind of a boundary edge case where we say this is at least suggestive of a depolarization effect for younger users, while for older users we cannot make any statement either from an identification perspective nor from a statistical inference perspective. Yeah. All right. Here's also an example. If you use a linear model, so if you impose a little bit more structure, then results become statistically significant. It's just again to get a little bit of an idea what's going on. But it's at least suggestive that we should maybe look in future interventions at this younger cohort and more powerful studies for the young users in particular. And it makes sense, right? Young users are probably more likely to change the view about the other side when they're being exposed to new information compared to older users that already have much more developed habits and beliefs and attitudes. Yes, and I think, Michael, how am I doing on time?
Oh, you're doing quite well. So yeah, 1 hour.
Okay,
yeah,
I think I'll skip.
Yeah, it's already 1 hour, so you have if you want to wrap up, I think it's fine.
Okay, so I think I'll skip the second application then. Maybe just briefly, we also find very interesting heterogeneity there and significant effects for particular subgroups on mental health, which are characterized actually by high socioeconomic status. So in terms of a conclusion, there's some open questions, of course. So now the theory is for IID data, but of course you would like to apply this to, for example, cluster structures or maybe other types of dependent data. Questions about whether we exploit the information in the most possible way is not addressed in this paper, but I have some follow-up work with Esbjørn Kaufmann, a PhD student of mine, and Sven Veljev, who is also at Aarhus University, where we address that question. And then some more technical issues that also have to be solved and extensions to maybe other problems than just bounds, but maybe also general sets in higher dimensional spaces for more complicated methods where we could also be interested in heterogeneity analysis as well. But, so there, if you would like to try out some of these methods, I have a very user-friendly, in my opinion, R package on my homepage, which essentially, you just put the data in, you specify some basic options, and you get these heterogeneous results plus confidence intervals. You can try that out, and I'm happy to help you also if you want to use that. Yeah, thank you very much for your attention. I'm looking forward to any questions you might have.
Great, thank you, Philip, for this very interesting and informative talk. Yeah, there are many interesting points you covered in the talk. Now we open the floor for Q&A. So if you want to ask a question, you can click on the raise hand button, or you can type your question in the chat box, or if you want just to speak up, you can also do that. Okay, maybe let me see. So maybe I can start with some questions. You mentioned this estimation, so I will start maybe from more technical part, right? So you will do the debiasing. Yeah, so my question is, if you consider, let's say, a very rich set of covariates to observe the X variable, I'm not very familiar with the kind of Facebook covariates. I suppose that sometimes you could have maybe a high dimension in this X. I mean, when you do this debiasing, do you consider, for example, the general, there's the recent paper on the auto debiasing, right? So you can have this rates representer, and then, what's going to be automatic debiasing? Or do you think your, debiasing approach is more efficient? Like, I'm just curious, like, yeah, because I do not see any like regularized estimation in terms of if you really have this dimension P greater than sample size. And in that case, you probably will apply some like a, I don't know, like a Lazo type or some type of regularization.
Yeah. So it's a good question. So the estimation of the Newton's functions, of course, is a crucial step because we have certain requirement how quickly they need to converge to how quickly the Newton's function converge to the truth in a standard debiased ML setup to actually achieve that in high dimensions. Of course, you need both. You need to restrict the class in which you're estimating, right, and then you need to pick the architecture for that particular class that you would like to estimate. Yeah. So let's say if I'm assuming a high dimensional sparse regression model, then to achieve the rates that I showed you earlier, need to have certain sparsity assumptions, which in the concrete case would be that the sparsity index of the high dimensional, let's say, parametric model is somewhere between so the true number of active regressors is somewhere between square root n and of order n, so smaller than n overall. So practically, same applies also if you think about random forests, right? If you make the random forest sufficiently deep and so forth, then under certain, for example, sparsity assumption, you have convergence guarantees for that. But in terms of the debiasing itself, right? So here we're, you can learn the Riesz representer for this linear moment function class in which the individual components also fall in that I'm discussing here, right? So remember, for the moment functions, I had these ratios So I'm doing two problems. I could also take the Lie type of moments and learn the debiasing for each component, and then combine it again in the non-parametric regression as I suggested it. But I don't need to do it if I have the analytical solution as well here. So that in terms of efficiency, this matters what type of debiasing, how do you do that explicitly, because there are actually infinitely many ways how you can do the debiasing here. But some exploit more information better than other. What I'm doing here is not generally semi-parametrically efficient except if you impose other additional assumptions on the GP. So this is what we try to address what we are addressing in the follow-up work. So there we come up with some slightly different functions that actually incorporate the uncertainty a little better, but they have the disadvantage of requiring more nuisance functions than the one that I showed for this approach. So there's a little bit of a trade-off in terms of, what you assume you can learn well and how efficient you overall can estimate a parameter.
Thank you.
Hi, Philip.
Hi.
Yes, I just have a question about the treatment effect for the Aarhus taker. So is that possible we can identify the average treatment effect or any types of treatment effect except to the Aarhus taker treatment effects, or maybe we can make a little bit stronger assumption, or maybe we do some other types of manipulation. Can we get more general average treatment effect and for your paper, or just we just can do the office takers treatment effect? Or
So in the paper, I'm explicit about the Orbis-take effects because those are the canonical ones in that literature on partial identification under sample selection. But in the follow-up paper, we provide also the relevant moment functions for the compliers and defiers. So everything I just discussed can be applied essentially the same way, just with different moment functions also for these two.
Okay.
The never takers, for them, you will, without additional assumptions, you will never be able to say anything because you never be able to observe them. So you based on that, you can say something about any aggregate of always takers, compliers, and defiers, right? So for example, the selected as a one example, or each group separately, but the average treatment effects of an arbitrary unit here, well, you can still do it, but the bounds will tend to be pretty wide depending on the shares, right? If it's very unlikely that you have never takers under monotonicity assumption, then the uninformative bounds for negative takers will not matter that much. But generally, the more you have of those, the wider things become, the closer they get to, for example, the support bounds of your Y upper and lower bound, something like that.
Okay, good. Thank you.
I may have another question relating to the real data study. So, I mean, can you go to this slide where you describe this observable? Yeah, so I'm wondering, do you select like a few observed variable X in a study, or I mean, do you use all the available data in terms of, so I mean, is this the variable that you got access to, or you do some kind of pre-screening on this covariance that you have?
So do you mean for the X or for the Z?
For the X, specifically for the X. I mean, Z, you may probably interested in certain aspects.
Yeah. So for the X, because this is essentially, building on this Levy study, I used all the information that he used in this rich specification because I wanted the results to be comparable. Of course, you can construct a little bit more. He also had a subset of users where they were opting into a Facebook module where you can collect more, online behavior information. But that sample was a little bit smaller, and then also, selected it again. So I didn't look at that data. I took basically all these baseline variables that he also used. So from the survey and Facebook, which included ideology, party affiliation, but also socio-demographic information, age, and the like. How much news do you consume? What do you think about the last president, and stuff like that?
I see. Yeah, so now in terms of your empirical finding, let's say if I'm a practitioner, I apply your package, it's very nice. But I mean, what is your take on, your estimated identified set and also this conservative, let's say, confidence band?
Mhm.
I mean, because sometimes when you say it's a conservative, right? I mean, in a way that people may want to have a sense of, how conservative that is, because I can see the difference. And sometimes, if they want to see, oh, maybe is this conservativeness is really, play a role in the heterogeneous treatment effect, probably they will focus on this red area. But I mean, people like me, I'm more conservative, so I just look at. But however, these two results could be, sometimes do not agree with each other. Yeah. So maybe what is your take on, kind of this conservative confidence span? Because I mean,
Yeah.
at least from this final result, I see there's some disagreement between this.
Yeah. I mean, so I mean, I would take this again, as I also described it, as a suggestive finding. I wouldn't say like, okay, we definitely know that this is a great nudge for younger users, but I would take this and say, okay, maybe my next intervention should be powered to detect effects, for example, for units who are maybe below the age of 30, and just collect more data for those units. And then, the good thing is the statistical uncertainty actually will become smaller as we collect more data. But the identification uncertainty, will not really. I mean, of course, there's finite sample variation there, but this is a fundamental problem that will not go away with more data. So it's something that is just there as a problem. But the blue one being far away from the red one, we can solve by collecting more data here. So in this particular instance, if I run a follow-up study, that's what I would do, right? I would take these heterogeneity groups and then try to find more powerful research design for that. Maybe as a slight additional remark, because a question might also be, okay, as a policymaker, let's say you get an identified set like that with the particular statistical uncertainty, should I now implement the intervention, yes or no, for let's say the younger users? And so this is basically the question about the policy allocation and decision making based on the results that we obtain that are set identified. And this is research frontier content, but there's some interesting new work being done in the direction in terms of what are the optimal allocation strategies for these kind of non-trivial, partially identified sets. So I recommend a recent paper by Olea, Jörg Stoy, and third co-author, who unfortunately I cannot remember, that was posted in arXiv end of last year on decision making under partial identification. They basically look at, okay, how can we use conventional criteria for statistical decision making to say something in setups where we get a set and a set that is also estimated with some uncertainty. And in this case, what you find is that certain rules that we would consider useful also in the context of classical treatment effect allocation tend to look quite differently in this partially identified setup. For example, certain minimax optimal rules will always have a certain share of randomization as an optimal decision rule. But this is research frontier, and I think this is, if you're interested in that direction, to do research yourself, I think there's a lot happening along that dimension. Because I think, so maybe to make a more principled point also, in many setups, we impose assumptions for convenience to get a point that is easy to communicate and to act upon, but it's actually not a credible assumption that we're making. So we should rather think about what assumptions are credible, what are we willing to impose, and then based on that, make the best decision given this information available. Like I'm not in favor of imposing very strong assumptions just to have something simple that might be just completely wrong. And I think assuming, for example, exclusion restrictions in a sample selection model is something quite strong that people are very often doing. And that's why you get a lot of contradicting findings, for example, using IV-based methods in many empirical studies. So this is an alternative to that. It's not replacing the other idea, but it's definitely an alternative.
Okay, thanks.
Any more questions?
If there's no other question at this moment, then let's thank Philip again for your wonderful talk. And so I know it's already late in Boston, so maybe we can end the webinar now. Thank you very much.
Thank you very much.
Right. Bye-bye.